Okay, so I just went in and had a look there, and not many people have the homework uploaded. So just to be clear, there was this homework, which most people have, which is great, from the 24th. But then last Wednesday I gave you this homework, which was the paper question based on Mechanics 1 Part 1 and Mechanics 1 Part 2. So this is what should be on OneNote. So I do have the solutions to this, but I'm not going to post them yet because not enough people have it done. So I didn't record the no homeworks, just to give you a little bit of a chance to get this on your OneNote. But can you please get this up for the 25th? And if you can, put the date on it. Sorry, I'm writing something here. So yeah, if you can, put the date on it as well, so I can figure out which homework is which. Now I know a couple of people did post the experiment, which is great because I do want you to do it, but that wasn't the homework that's due. That's just going to be the next experiment. It's literally the next class we're going to do when I come back. All right? Which is what? Next Wednesday? Okay. So I'm going to keep going with the chapter. Right. So we're moving on to acceleration due to gravity. Okay, so I always hate explaining these things over a video, but it should be easy enough to explain. If you drop, like they have here, a coin and a feather. So if you stood at the top of, I don't know, a tower. Okay, and the same person stood at the top of both towers. And off this tower, they threw a coin, and then, I don't know, 5 minutes later or something, they threw a feather off this tower. The question is, would they hit the ground at the same time? Now, I think the logical answer, and most people will come up with this answer, is no, they won't hit the ground at the same time. But I suppose what I want to challenge you with is the fact that, why don't they hit the ground at the same time? Because they're both on the same building, on the same planet, so they both have the same forces acting on them in terms of the down forces acting on them, the gravitational force acting on them. So what is it that causes them to not hit the ground at the same time? So the sorry, multitasking here again. The thing that is different between the two scenarios is air resistance. So because the coin is more compact, more dense, has the bigger mass, it's heavier, it's going to cut through the air much better than the feather, which is, you know, only short of being designed to catch air. It's got a big surface area, it's got like flappy edges, it's going to catch loads and loads of air. So essentially what I'm saying is that when these objects fall, the down force on them is exactly the same. But they won't hit the ground at the same rate or at the same time because the air resistance will have a much bigger impact on the feather. And the air is the air resistance, or the air friction, whatever you want to call it, is the force that opposes gravity. So if you want to see the true sense of gravity on Earth, the only way to really see it is to remove the air. So now give me a second. I'm going to try and put this video in and then play it. Physics. Okay. Oops. Okay. So
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems, and that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one, and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So, in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCB 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Look at that.
They came down exactly the same. Wow.
Look.
That's right there. How they hit right there.
Exactly.
Back on the side.
Exactly.
Okay, so that's a really good video to demonstrate accelerating due to gravity in its purest form on Earth, because they had the very special situation that they'd set up there in NASA where they could basically do the entire experiment in a vacuum, remove the air, so then when you don't have the air resistance, you can see the true force of gravity acting downwards. And then it wasn't a coin, it was a bowling ball or whatever, and a feather do actually fall and hit the ground at the exact same time. Okay, so gravity to 1 decimal place anywhere near the surface of the Earth is 9.8. Now, the way we think about this is it's a force causing an object to accelerate. Ooh. Okay, so it's an acceleration, and that's why the units are meters per second squared. Okay, so G is 9.8. You can see where we are So that's the closest kind of point of reference we have. So acceleration due to gravity in Dublin when we do our experiments is about 9.81 meters per second squared. And it does vary slightly, but to one decimal place anywhere on the surface of the Earth, it is 9.8. So that's the constant that we use. We will we'll learn formulas and stuff to prove this point here that I have highlighted, but gravity, or the value of G, decreases as you move away from the center of the Earth. And we know that on the moon, gravity is, considerably less than it is on Earth. You've probably at some point in your life seen video from inside the International Space Station. You can see that they have, reduced gravity, and they're like floating around on the International Space Station. And gravity on the ISS is about 90% of what it is on Earth. So, it's not nowhere near what it is on the moon, but it's still severely reduced. Right, so as I said, acceleration due to gravity is just an acceleration for a given object falling in a given situation. It's going to be constant. So that means we can use our UVAST equations. So that's what I'm going to do here. So an object is dropped from the top of a building which is 30 meters high. With what speed does the object hit the ground? And how long does it take the object to reach the ground? So again, kind of a not very well labeled two separate questions. Okay, so the object is dropped. I'm going to put my UVAST down. So it's dropped means it was held. So it was not moving and then it was dropped. So that's 0. And with what speed does the object hit the ground? That's v. Acceleration, so it's being dropped, which means it's falling with gravity. So that's 9.8. S is the displacement or the distance. It says over here that the building is 30 meters high. And how long, last bit is time, and we do have a how long question, so we do want to know the time as well. Okay, so obviously we have two variables. We're not going to solve both of them in one go. We'll start with what I've called question 1. So that's kind of like these ones. So go into your formula and tables book, have a look at your UVAST equations, but v squared equals u squared plus 2as. Becomes v squared equals 0 squared plus 2 times 9.8 times 30. So the 0 squared is just 0, and the other thing is 588. And then if I square root, I get v is 24.25, and that's a velocity, so it's meters per second. And then question 2 is time. So there's probably a good few you can use here. You go with v equals u plus at. So I have velocity which is 24.25, but I've actually kept the number on my calculator, which is going to be a little bit more accurate. So that's what I'm going to use. U was 0, A was 9.8, and T we don't know. So 24.248 is the number on my calculator. This is just 9.8T, and then we divide by 9.8. So I'm getting 2.47. And units for time, seconds. Yeah, we'll do this one. So the next one is kind of similar. Object falls from the top of a building, strikes the ground 5 seconds later, find the height of the building. So again, it's u equals 0. It's falling, so A is 9.8. 5 seconds is your time. And find the height, we're looking for S. So S equals ut plus a half at squared, we'll get yes there. Now this one I want to do because, the stone has been thrown upwards. Okay, so I just wanted to show you how you handle this one. Okay, so upwards with an initial velocity of 20 meters per second. So it literally says it's the initial velocity, so u is 20. Now, find the greatest height reached by the stone. Okay, so I want to talk to you about this greatest height thing. We do this in maths as well. So if I'm standing here with the stone and I'm going to throw the stone upwards, the stone's going to go up because I've given it enough force to overcome the force of gravity on this, like the weight of the stone acting down. So I'm going to throw it up. It's going to go up, but it is working against gravity. So it's only going to go up a certain amount. And then once it gets to that height, it is going to stop for a moment and then it's going to fall back down. Yeah? So at the greatest height, for an instant, the speed equals 0. And you have to use that in the questions. Okay, so at the greatest height, the speed equals 0. So my final speed is going to be 0. Acceleration, so it's going against gravity. So the way we do that is with our sign. So we say that instead of it being picking up 9.8 meters per second for every second it falls, it's going to lose 9.8 meters per second for every second it climbs. Okay, S is what we want, and time, I mean, we're not given it and we're not asked for it. Do we need it though? I don't think so. U, V, A, and S, I think we can do V squared equals U squared plus 2AS. This is going to be 0 squared. This is going to be 20 squared. This is going to be 2 minus 9.8 and S. So 0 equals, we have 400. 2 times minus 9.8 is minus 19.6, and then S. I'm going to multiply by S as well. I'm going to add 19.6S to cancel this and add 19.6S over here. That gives me 19.6S equals 400. And then to isolate my S, I'll divide by 19.6. So I get the distance is 20.4. And that's a displacement or a distance, so it's meters. All right. So that's just giving you an idea of it's still UVAST, you still do it the same way, you still identify your variables. It's just because this is a vertical acceleration, either with gravity or against gravity, your A is a constant. Either 9.8 if the object is falling, or minus 9.8 if the object is being thrown upwards. Okay, so, oh no, sorry, I had definitely picked a few questions. Okay, let's do 2. Okay, 6 and 7. Okay, so those 3, question 2, question 6, question 7, and it's Wednesday, so they're actually due for next Monday. Yeah? Okay. So please, if you're behind or you don't have the last set of homework up, will you please make sure you have that up so that when I'm checking for Monday's homework, I should be able to see this homework from the 25th as well as the homework I just gave you there. Okay? Okay, cool. I'll talk to you again on Monday.